So how do we satisfy those constraints? Okay, here is a theorem. Okay, suppose no negative wave cycle exists in a constraint graph, then the constraints are satisfiable. Okay, how do we prove that? First, okay, let's say this is like the constraint graph. Okay, assume there's no negative wave cycle in this constraint graph. Okay, and then we especially add a new vertex S. Okay, this new vertex X is different from all these vertexes. Okay, with a zero weight edge to each vertex Vi. So it's something like this. Okay, so it does not change the original graph. It's just like we add this new node and then add a zero weight edge to each of the vertexes. Okay, and because this graph, if the original graph does not have negative weight cycle, after adding S and these zero weight edges to the graph, obviously it does not contain negative weight cycle either, right? Okay, it's impossible. Okay, so having said that, okay, here we say, okay, if there's no negative weight cycle introduced in this graph, there must be shortest path, right, from node S to every other node. To every other node, we have shortest path, right? Okay, I mean this can be done by Bellman-Ford, right? Okay, because remember, like we have to use Bellman-Ford because there may be negative weight edges, right? It's just we don't have negative weight cycle, but it doesn't mean we have no negative weight edges. Okay, so because I mean it's not like all the weights are positive, so we have to use like Bellman-Ford. Okay, so we claim that assignment xi equal to delta. I mean, this is like the shortest path weight, right? From S to Vi. Okay, if we assign xi to be the shortest path weight from the source node S to the vertex Vi, okay, it's going to solve the constraints. Okay. The idea is like this. If we consider any constraint, this is any constraint. Say this is Vxj minus xi smaller than or equal to Wij, and it's it is shown here, right? It is shown here. We have Vi representing xi, Vj representing xj, okay, and we have edge from Vi pointing to Vj with weight Wij, right? That's exactly what I just told you, okay, how you convert each constraint into a graph format, right? Okay, and then if you consider the shortest path from S to Vi and Vj, okay, this is shortest path from S to Vi, this is shortest path from S to Vj. Okay, we know from the triangle inequality, okay, I mean the path also has triangle inequality, right? Okay, this triangle inequality gives us the shortest path from S to Vj, okay, this one is going to be the weight of shortest path from S to Vj, this one, must be small or equal to this one plus this one, right? Okay, this one, shortest path weight from S to Vi plus this is the Wij. So so now if we assign this one to Xj, this one to Xi, then it exactly solve this constraint, right? It solved this constraint exactly, right? Right? So, and in this discussion, we do not specify which particular constraint we are talking about. This discussion is valid for every constraint, right? Okay, if this discussion is valid for every constraint, then basically this assignment will satisfy every constraint, right? Okay. So actually, let's go back to this particular example. Let's construct a graph. Okay, 3 nodes. Okay, construct a graph. X1, X2, X3. So we have V1, V2, V3. And then, okay, so X2, X2 point to X1. And we have 3 there. It's representing the first constraint. And then X3 pointing to X2. V3 pointing to V2 is -2, right? And then we have V3 pointing to V1. And with a weight 2, right? And then we have a node S. They are 0, right? So obviously there's no negative weight cycle here, right? So what is the shortest path weight from S to V1? It's a 0, right? To V1 is 0. Let me see. Yeah. And what is shortest path from S to V2? Well, it looks like it's 0, too. And what is shortest path from S to V3? It's this one to here. It's -2, right? 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 So if we assign 0 to both V1 and V2, so 0 minus 0, 0 is smaller or equal to 3. That's good. And V2 is 0. Minus X3 is, V3 is -2. So this one is X2 minus X3. X3. Oh, I'm sorry. I make it wrong. Okay. The pointing direction is here. So it should be 0, -2. So this is -2. This is 0. Right? It should be like that. Okay. Okay, I made a mistake. Okay, so if V1 is 0, V2 is negative 2, V3 is 0. Okay, 0 minus negative 2 is 2. 2 is smaller or equal to 3. That's true. And x2 is negative 2. And x3 is 0. Okay, negative 2 minus 0, small or equal to negative 2. Okay, x1 is 0. And x3 is 0. 0 minus 0. 0 is small or equal to 2. So we found a possible solution to these constraints, right? Okay. So we know the Bellman-Ford algorithm can solve a system of n difference constraints. Remember, we call this particular constraint as difference constraints on n variables in big O n times n times. Okay, because like we have n number of ages. We have n number of ages. We have n number of variable, or in other words, n number of vertices. Okay, and remember, like a Bellman-Ford algorithm, time complexity is v times e. Okay, so that's n times n. Okay, so single source shortest path is a simple LP problem. Okay, so in fact, Bellman-Ford maximize. Okay, previously we said this is like a satisfiable problem, right? But actually, Bellman-Ford, this solution, the solution provided by Bellman-Ford, is going to maximize x1 plus x2 blah 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 plus xn, subject to the constraint xj minus xi small or equal to wij, and the xi smaller than 0. Okay, this one, I mean, I'll leave this one for you, I mean, as an exercise. I mean, you can remember, like, I gave you an exercise last week, right? Okay, we still have one last exercise, okay? After today, tomorrow, next week, okay, after we finish next week's lecture, okay, NP complete, I'm going to give you like programming, the homework assignment for, this stuff, okay? So this one, and Bellman-Ford also minimize the max xi, okay, minus min xi. Okay, again, this is left as an exercise for you, okay? So anyway, actually Bellman-Ford algorithm provide the solution, okay, also for like like a linear programming, okay. I mean, where like we have like something we want to maximize, okay. So with that in mind, okay, another possible application, because you know like the Bellman-Ford algorithm can help you to solve like a special case of linear programming, right? So this also has another application to VLSI design, okay? So in like an integrated circuit, I mean, if you have some features, and those features, okay, requires minimum separation. Okay, we call that minimum separation as lambda. Okay, and also we want the minimum everything to be compact. Okay, because we want to design the circuit as small as possible, right? Nowadays you want to have a very small circuit design. Okay, That's what we call VLSI, right? Very large. Okay, that's where like a very large stands for. So compact in one dimension. So we, of course, here, okay, we confine our discussion in one dimension. In one dimension only. Okay, this discussion can be generalized to more than one dimension, but let's confine our discussion to one dimension. Okay, the space between the features of a VLSI layout without bringing any feature too close together. So if you try to represent such a constraint, okay, because it's one dimension, right? So you try to measure it by, by variable. Okay, so here is x1. This is feature 1. You have x1 here. Feature 2, you have x2 here. So the x2 minus x1 is going to be greater or equal to d1. d1 is like the size of this feature 1 plus a lambda. This lambda is what we call the minimum separation, right? I mean, you can represent, this constraint as like a difference constraint that we just talked about previously, right? Okay. So this is for a particular feature, right? We could have many different features, okay? Each one represented by something, like that. Okay? So you are going to have like a lot of this constraint, just like what we have here. Sorry. No. Something like this. Okay. And then remember, I also told you that the Bellman-Ford solution it provides is going to minimize the max xi minus min xi, right? Okay, so it's going to minimize the difference of like your largest assignment and the smallest assignment. And if you put it in like a VLSI problem, okay, then, okay, the Bellman-Ford minimize this one, right? Which compacts the layout in X dimension, okay? In X dimension, okay, because the Bellman-Ford solution is going to minimize this one. So it's going to make your circuit design as small as possible. That's exactly what we are looking for. Okay. So just want to give you important application, because now in Taiwan, like everybody want to work for like TSMC, right? TSMC or like 那个叫什么的，卖干能叫什么来着？那另外一家什么？那个联发科啦，对啊，都在做 circuit design 嘛，对不对？啊 ，circuit design，this is like something about circuit design. Okay. Okay, that's it for this lecture. But we are not done yet. Okay, as I told you, like the graph. Okay, the shortest path actually has 3 lectures. We only talk about 2 lectures. We only finished 2 lectures. So now we are in a position to talk about the 3rd one. Hmm? 今天 NBA 谁赢了？没人知道吗？ Okay. So previously we are talking about single source shortest path. Okay. So this section is also about shortest path, but it's all pairs shortest path. Okay. So for the single source shortest path, okay, if all your edges are non-negative weight, then you can use Dijkstra, and the complex is this one. Okay, this is the one without using the Fibonacci heap. Okay, after all, I told you like Fibonacci heap was not covered. Okay, even though Fibonacci heap is able to bring the complexity further down a little bit, but we didn't cover Fibonacci heap. So this is like if you use like a heap, just regular heap, then this is what you get. And if you are not talking about non-negative edge, for general case, okay, as long as you don't have negative weight cycle, then in the previous slide, I mean, the previous lecture, we know the Bellman-Ford is going to help you to get like from a single source to all the other nodes. I mean, the shortest path. I mean, find all the shortest path to the other nodes in big OVE time. If this DAG is directly acyclic graph, there's no cycle. If there's no cycle, the complexity is going to be big O V plus E. So why is this that? I mean, like that. I mean, because we didn't cover this part. Okay, but it's not that difficult. But it's just we don't have enough time to do that. So if we have time, we'll come back to talk about this. But the idea is that, I mean, you guys have learned the topological sort, right? In the data structure, you should have learned topological sort, right? So first, you can try to put your graph into a topological sort order, and then do the edge relaxation in that order. Then you guarantee you are going to have a much better complexity. Okay, because I don't have enough time, so I will end here. But if you are interested, I mean, if we have time, I will talk about this. If we don't have time, you can check it out. Like there are, I mean, references that you can find like online, very easily. Okay, but anyway, okay, this is of course much. I mean, DAG has a lot of constraint. I mean, it doesn't. You require the graph has no cycle at all. So this is like a much more higher demand than non-negative edge weight. Okay, so you can see that if you have that the graph, I mean finding the shortest path, it's going to be much cheaper. It's V plus E is compared with all the other, it's much lower. The order is much lower. But all these algorithms help you to find from one single source for the shortest weights, a shortest path to all the other nodes. Okay, but how about if you want to find all pairs shortest path? If the graph has no negative weight, no negative edge weight, then you could apply Dijkstra algorithm V number of times. Basically, you just try to use every node as a starting node, okay, and then run the Dijkstra algorithm. So it's going to be E plus V log V times V, right? So that's the result. VE plus V squared log V. Okay? Should be very easy to understand. I mean, it's just, what should I say, like a brute force, run the Dijkstra. I mean, like from every single node. That's it. But if you this actually is cheap enough, you know. I mean, even though this looks like a kind of stupid approach, okay, it's not. It doesn't look like it doesn't sound like a smart approach, but it is actually not that bad, okay. This also, by the way, this also tells you how good Dijkstra algorithm is, okay. I mean, when we first talk about Dijkstra algorithm, okay, you may not appreciate how quick it is, okay. When you look at the big O E plus V log V, you probably don't feel like it's very, very good. But actually, it's pretty good. Even if you run the Dijkstra algorithm V number of times, it is still considered quite, I mean, good. Okay. But anyway, okay, that's the non-negative age weight situation. Okay. For general case, we have 3 algorithms that we are going to cover. That's why I kind of feel like I may not have enough time to cover everything. But anyway, I will give it a try. Okay. So, general case, what is general case? General case is like you could have negative weight ages, right? But you don't have negative weight cycles, right? Okay. So it's the input is a directed graph, okay, where you have n nodes and with age weight, okay, function, blah 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 blah. Output is because it's like all pairs shortest path. So that is, you know, because you need to represent like all the possible pairs, right? So the easiest way is to represent the result by an n by n matrix. Okay, so for example, like an Aij to represent from Vi to Vj the shortest path weight. Okay, and remember this is the directed graph, right? So Aij is not the same as Aj. Okay, remember what I just said, like Aij represent like the shortest path weight from Vi to Vj, right? Because it's a directed graph. So from the shortest path from Vj back to Vi obviously will be different, right? So the weight, okay, the shortest path from Vj back to Vi, which is represented by Aj, okay, it should be different from Aij. Okay, just want you to understand that. Okay, so delta Ij, okay, it represents like you know, for all Ij, okay, in Vi. This is, I mean, just what I said, Aij, okay, in your matrix. Aij represents the delta Ij. So, this is our input. This is our output. Okay. The most straightforward idea, okay, is to run Bellman-Ford like from every vertex. It's just like the simple idea I just mentioned for the Dijkstra algorithm, right? We run it from every single node. Okay, so if we do that, the time complexity is going to be V squared E, right? Because original Bellman-Ford is VE, right? So now you run it on every vertex, so it's like V squared E. So if it's like you know, dense graph, okay, dense graph means like the age is like in the order of n squared, right? Okay, if it's in the dense graph, then the time complexity is going to be n like to the power of 4. Okay, in the worst case. Okay, is it good enough? Actually, it's not that bad, but really like n to the power 4 is really not what we are looking for, okay? But at least it's a, as I say, it's a good first try, okay? So here, okay, let's try to use dynamic programming, okay, to solve this problem, okay? Let's consider the n by n weighted adjacency matrix. I mean, Aij, A equal to like lowercase aij, okay. This Aij represent like a weight, okay, of the edge ij, okay, if there's an edge between node I to node j, okay, obviously. Or infinite if there's no edge. And define Dij m to be the weight of the shortest path from I to j that uses at most m edges. So this m, I want you to remember, this m means like from node I to node j with at the most m edges. Okay, and obviously the adjacency matrix is going to be like this, right? Okay, according to the definition of adjacency matrix, it is exactly the same as the Dij0, right? Okay, and for m equal to 1 to blah 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 to m minus 1, remember like I told you like if it's like if you have no negative weight cycle, then the longest possible weight possible path between longest possible shortest path, okay, between two nodes is n minus 1, right? Okay, so that's why like m, I mean, is from 1 to blah 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 to n minus 1. Okay, so it's going to be what? Okay, Dijn. I'm sorry, I mean, this is like not, it doesn't look very good, but you get an idea, okay? Dijn, it's going to be minimum k, okay, the dik n minus 1 to dkj, akj, I'm sorry. Let me, where's the, here. Do I? Okay. Let me write it here. This is mean k, because we have k such pair. This represents the edge from k to j, okay, the weight of the edge from k to j. Okay, this is like the shortest path from I to k, okay, with n minus 1, using n minus 1 edges, okay, plus this one. And we are looking for the smallest one from all these possible combinations. Okay, I'm sorry it doesn't look good enough, but you get my idea. Okay, so this is, if we represent it by a graph, it's going to look like this. Okay? So you are trying to find the smallest value out of this, all the possible combinations. And each of these is basically relaxation. So you just use a loop to run through all this, and basically, okay. If so, you may ask, what is this going to be represented in there? Okay, it's here. Okay, if none of this condition is met, then it's this path. You use n-1 edges. Okay, if one of them is satisfied, you replace this one by one of them. If none of them satisfy, then it's this edge. Okay. So no negative edge weight cycle implies like this shortest path from I to j is going to be shortest path ij n-1 blah 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 to n and n plus 1 blah blah blah. So if as I said, like the shortest path, okay, between I and the j, the longest possible shortest path is n-1, right? You have n-1 edges between them at most. And it's obviously going to be the same regardless of how many additional edges you provide. So n-1, n plus 1, I mean, they are all the same. Right? Right? So once you know that, okay, so you know we are, I mean, when you do the matrix multiplication, okay, we are, like this is very simple. Okay, when you compute A matrix times B matrix, okay, if CAB are n by n matrices, then Cij is going to be something like this, right? You know that, right? I mean, everybody knows that, right? Okay, so such a computation takes n cubed, okay, using the standard algorithm, right? Why? Because like it's well, what should I say? You have like n by n squared such elements to compute, and each element takes linear time to compute. So it's n squared times n is n cubed. Obviously, like we previously talked about a divide and conquer approach, right? Did we? Like you could try to reduce this complexity from n cubed down a little bit, but yeah, I mean, if you use the standard algorithm, yeah, it's n cubed. Okay. So what if we map the plus to min and the times to plus? Okay, so it's going to be Aij plus Bkj. Okay, I mean, and the summation becomes like we find the minimum out of them. I mean, it doesn't change the complexity. Okay, it doesn't change the complexity, but it helps us to deal with this one. Okay, because look at here. This one is like from one. You can consider this one from one matrix. This one from another matrix. Okay, so basically what we are doing is we could use the matrix multiplication algorithm to do what we want to accomplish. Okay, so the D, okay, M could be D n minus 1 times adjacency matrix. Okay, now at the beginning, I mean, it's the D0 is going to be identity matrix. Okay, this initial case, okay, and then after the first multiplication, it's I times A is A, right? Which is very, how should I say, like very appropriate, because like if you only need one, if you are only able to use one H, then obviously like the D0, sorry, D1 is going to be exactly A, right? I mean, according to the definition, it should be the same. So it's going to be A identity times A. That's going to be I times A is going to be A. So, okay, once you do that, okay, this structure is called closed semi-ring. Ring is one algebra structure, okay, just like a group ring field, okay. Those are like how we discussed like in like a mathematics department algebra class, but but I don't think you need to consider this stuff. I mean, because you guys are not in the math department anyway, okay. So consequently, so we have D1 equal to D0 times A, which is A to the power of 1. D2 equal to D1 times A is A squared. D blah blah blah, Dn minus 1 is equal to A to the power of n minus 1. So basically, okay, so Dn minus 1 is going to be, the content is going to be delta Ij. Okay, this time is not a regular multiplication, matrix multiplication. It's you change like the multiplication by addition, and you change the summation by the mean. Okay, so even though we use the dot, but they are not really matrix multiplication per se. Okay, but you get the idea. Okay. So this one, okay, so how much time does it take? Because each computation take n cubed, right? And you need to do this, n minus 1 times. So it's like n times n cubed, so it's n to the power 4. Well, you are going to be surprised to find that this is no better than you run the Bellman-Ford algorithm n times. Okay, because it's n to the power of 4. That is also why previously I told you guys, well, Bellman-Ford algorithm is not, running Bellman-Ford algorithm n times is not necessarily too bad, right? Remember I told you that? Okay, after you do all this, you find that it's still n to the power of 4. But we are able to do something to make it a little bit better. Okay, let's take 10 minutes break. When we come back, we will continue the discussion here. Okay?